This is the first of two lectures discussing the material in Chapter 9. We're going to talk about hypothesis testing. So we're going to break this up into two parts, and in this presentation I'm going to cover some basics of hypothesis testing, including how we formulate the null and alternative hypotheses and what those things are. And I'm going to talk about the types of mistakes that we can make when we undertake hypothesis testing, so-called type 1 and type 2 errors. And it's important to understand that we're going to be making decisions about population parameters from sample evidence. So, I mean, there's always the chance that we could make a mistake, and we should understand what those types of mistakes are and which types of errors we can carefully control and which ones we cannot. This chapter in your book includes hypothesis testing surrounding both hypotheses about the population mean and the proportion. I'm going to cover two examples using the population mean and one example using the population proportion. Each of the examples that I go over will be slightly different from the other two. I'm not going to cover the case where we know the population standard deviation, however. I'm just going to cover the case of the population standard deviation unknown and estimated from sample data. So the big difference here in terms of the population mean is that if you know the standard deviation of the population, if you happen to be so fortunate, you don't need to use the t-distribution. You can use the standard normal distribution. So hypothesis testing in general is going to be used to determine whether or not some statement about a population parameter should or should not be rejected. If you want to, you can think about an analogy between somebody being arrested in the U.S. justice system. Right? So, you know, the question in court is whether or not there's enough evidence that an individual committed a crime such that, you know, they should be convicted of the crime. And so, you know, with hypothesis testing, we have what we call a null hypothesis. And that's sort of the straw man. That's the tentative assumption. And we're going to look for the evidence to kind of weigh up against the null hypothesis until there's enough evidence against it to reject it in favor of an alternative. So coming back to the legal system, the null hypothesis in our legal system is that somebody's innocent until they're proven guilty, until there's enough evidence to prove them guilty. Right, we need enough evidence so that they're guilty beyond a reasonable doubt, I believe is what the law says. Okay, so the alternative hypothesis is the opposite of the null hypothesis. So in the legal example, if the null hypothesis is that you're not guilty, then the alternative obviously is that you are guilty. And we put the burden of proof against that alternative hypothesis. We start out with the assumption that you are innocent and then ask the courts to prove that there's enough evidence to convince a jury that you're guilty. We do something similar with hypothesis testing and statistics also. So the hypothesis testing procedure uses data from a sample to compare these two competing statements and decide which one seems to be more consistent with the sample evidence. In the same way that in a courtroom you take an individual and there are two competing sides, right? There's the defense and the prosecution, and you listen to all of the evidence. And then if you're on the jury, you weigh that evidence and you decide whether or not to reject the hypothesis that the individual is innocent and convict them of the crime. Okay. So it's a nice analogy for thinking about the different issues that pop up in hypothesis testing. So to bring in an example that's a bit more quantitative and consistent with the type of work that we often do in statistics, let's imagine that there's a claim that the average IQ is equal to 100, and we want to test that claim. So what we're going to do is we're going to go out and administer 150 IQ tests to 150 randomly chosen individuals and calculate a sample average IQ test score. We find that, let's say that that's 108, and that the sample standard deviation in the population is equal to 38 points on that test, 38 test points. So that's the population standard deviation. Okay, we had to estimate that. We don't know it, so we'll be using a t-distribution here. So the question is 108 average in the sample, is that enough to conclude that average IQ is greater than 100 points. Because we know that when we go out and we collect a random sample of 150, we're not going to get a sample average that's exactly equal to the true population parameter. And sometimes we could overstate it a little bit with the sample. Sometimes we could understate it. And the question is 108, larger than 100 by enough in order to really conclude that there's strong evidence against the hypothesis that average IQ is equal to 100. Answering these types of questions is really at the heart of inferential statistics and statistical decision making. So there are three ways that we can formulate a hypothesis test. There are one-tail tests. There are two examples of these. I'll cover the middle one first. And then there are two-tail tests. So, with our one-tailed test, which is a lower-tail test, we're going to find evidence against the null hypothesis when our sample value is far below the hypothesized value, right? So that means that the alternative hypothesis, our research hypothesis, if you will, which we should put the burden of proof against, would say that average IQ is less than 100. So that might be the desired research result. And then the null hypothesis is, of course, stated as the opposite, that the average IQ is greater than or equal to 100, right? And so the burden of proof is put against the alternative hypothesis here. And we won't reject it unless we get a value in our sample of an IQ test that's small enough compared to the hypothesized value. That what that's going to lead to is a very small test statistic. And we're going to be in the left-hand side of the distribution of the test statistic, and that's why we call it a one-tailed or a lower-tailed test, or sometimes a left-tailed test. If you just reverse the sign of everything, you get an upper-tailed test or a right-tailed test. The null hypothesis there would be, for example, that average IQ is less than or equal to 100, and the alternative is that it's greater than 100. Right? So if we desired to show, as a research hypothesis, that average IQs are actually greater than 100, we would state that as our alternative, put the burden of proof against ourselves, and require a lot of sample evidence against the null hypothesis, which is stated as the opposite, which is that average IQ scores are less than or equal to 100. And then there's always the possibility of doing a two-tailed test where the null hypothesis is that average IQ is exactly equal to 100, and the alternative is that it's not. Okay, and there we're going to have two different tails that we're going to be concerned with, because either a really large sample value of the mean average IQ test is going to cast doubt on the null, but also a very small average IQ test score relative to 100 is going to cast doubt on the null. So on both sides, so we have a two-tailed test. So, whenever we do these types of tests, there's always the possibility that we could make a mistake. And the first type of mistake we can make is one that we can actually control for. It's called a type 1 error, and it's rejecting the null hypothesis when it's true. So going back to my analogy in the courtroom, a type 1 error it can be pretty devastating, right? Because if there's a type 1 error, what you're doing is you're taking the null hypothesis that somebody's innocent and you're rejecting it when in fact they are innocent. You're convicting an innocent individual, right? So, there's always that possibility in court, we know, unfortunately, and there's always that possibility in hypothesis testing as well. The probability of making this type 1 error is what we call the level of significance, and actually you've seen it before when we did confidence intervals. It's what we called alpha there. So alpha is our level of significance. Okay, so we can directly control for the probability of making a type 1 error. We could just decide that, we're only, say, 5%. We're only willing to take a 5% chance of making a type 1 error. And if the null hypothesis is true, we can construct our test statistic and our hypothesis test so that we pin down that probability of a type 1 error. So the types of hypothesis tests that we do in this book only control for a type 1 error. Pretty easy to control for that. These are called significant tests. They're the most common type of hypothesis test. Another type of error that you can make is a type 2 error, and that's accepting the null hypothesis when the null hypothesis is false. So, if you were looking at somebody who had committed a crime, right, and they actually were guilty, but you let them off, right, because you failed to reject that null hypothesis when in fact the null hypothesis was false, you would be making a type 2 error. Okay? Type 2 errors in statistics are more difficult to control for. I'll give you a little bit of intuition as to why. Going back to our IQ example, we don't know the true value of IQ in the population. That's why we took a sample and we're doing statistics. But let's just say that hypothetically that the true value of the IQ, average IQ in the population, let's say it's actually equal to 120 and we're hypothesizing that it's equal to 100. Well, that's a really big gap between 100 and 120. That's pretty significant. So it's quite likely that our sample is going to cast a lot of doubt on our null hypothesis. It's pretty unlikely that we're going to make a type 2 error and we're going to accept that IQ is equal to 100 when in fact it's really not. It's equal to 120. The data is probably going to do a pretty good job distinguishing in that case between the null hypothesis and the actual underlying value of the population parameter, right? So that is a pretty powerful test in that case. But let's suppose instead that we still hypothesize that IQ test scores are equal to 100, but the true IQ test, average IQ test score, isn't equal to 100. The null hypothesis is false, but it's pretty close to the hypothesized value. It's 102 instead of 100. Now the test is going to have a lot more trouble distinguishing and a much greater probability of making a type 2 error because the sample that we pull is much more likely to be consistent with evidence that would be consistent with a sample drawn if the true population parameter were equal to 100, even though it's not, right? So, the test isn't going to really be able to distinguish between a false null hypothesis of 100 and a true parameter value of 102 as easily as it's going to be able to distinguish between a false null hypothesis of 100 and a true population parameter of 120, which is a much bigger distance away from 100. Okay, so that's why type 2 errors are difficult to control for. So, we can't really control for it, but we try to at least remind ourselves of this issue by never accepting the null hypothesis. We just fail to reject it. So, just in a table, what we just talked about. If the null hypothesis is true, right, and we don't reject it, we've made the correct decision. But if the null hypothesis is true and we reject it, we've made the type 1 error. We've rejected the null hypothesis when it's true, right? So this would be a type of error that we can control for with alpha, our level of significance. Now, if the null hypothesis is false and we reject it, of course, we've made the right decision. But if the null hypothesis is false and we fail to reject it, we've made a type 2 error now. Okay, and that's the one that's a little bit harder to control for. I'm going to break hypothesis testing down into 5 steps for you. First, we're going to develop the null and alternative hypotheses, of course. Step 2 will be to specify the level of significance. That is, how willing are we to risk making a type 1 error. Then we'll collect a sample of data and calculate the point estimate and the standard error of the estimate. Those two pieces of information together with the hypothesized value when the null holds with an equality are going to be essential to calculating the test statistic. That's what happens in step 4. And then finally in step 5, we'll complete the test by determining if the null hypothesis should be rejected. There are 2 equivalent approaches, just 2 different ways of looking at the same information. One's called the p-value approach and the other one is called the critical value approach. So hypothesis testing, example 1, okay, we're going to do an upper tail test. So with my upper tail test, I'm going to state the null hypothesis that the average IQ test score is less than or equal to 100. Okay, I'm going to put the burden of proof against the alternative hypothesis. My research hypothesis, what I'd like to show is that the average IQ test score is greater than 100. So I make that my alternative hypothesis. Now I'm going to be interested in how the test statistic is distributed when the null hypothesis holds within equality. Remember, the equality always shows up in the null hypothesis. So step 2 is to specify the level of significance. So I'm going to say here that I'm just willing to make a 10%, take a 10% chance of rejecting the null hypothesis when it's true, of rejecting the hypothesis that IQ is less than or equal to 100, right? When it's actually less than or equal to 100. Okay, I'm going to fix that at 10%. Now I'm going to go out and I'm going to collect sample data and calculate the point estimate and the standard error of that estimate. So you already know I have 150 IQ test scores. The average is 108, and the population standard deviation is 38 points. To get the standard error of the estimate, which I need to calculate my test statistic, I need to take that 38 and divide it by the square root of 150. That's the sample size. We've covered that before, the equation for the standard error of the estimate when we're talking about the sample and mean. And what we get is 3.1. Okay, so all that information is going to show up in the calculation of the test statistic. Basically, the components are the 108, the 100 value under the null hypothesis when it holds with equality, and of course the standard error. So here's the actual test statistic and the way that it's calculated, and I filled the numbers in down below here for our example. So just first focus on the top formula. What shows up in the test statistic here is X bar. That's the sample estimate of the population parameter. In our case, that's 108. Okay, and so what I'm doing is I'm taking the difference between 108 and my hypothesized value. Now, if X bar is a lot bigger than my hypothesized value, then I'm going to get a really large t-statistic. You can see that, and that's going to cast a lot of doubt on the null hypothesis, because getting that value of the t-statistic would be pretty unlikely if the null hypothesis were true. So I'm going to reject the null hypothesis in this case if t is really large. But I can't just take the difference between X bar and my hypothesized value. I need to standardize it. I need to put it in terms of standard deviations. The appropriate standard deviation here is the standard error of the estimate. So S divided by the square root of n. So it's 108 minus 100, that's an 8-point spread, divided by the standard error of the estimate, which is 3.1, right? My sample average is 2.58 standard deviations beyond the hypothesized value of 100. And the question is that enough standard deviations above the hypothesized value of 100 to reject the null hypothesis if I'm only willing to make a 10%, take a 10% chance of making a type 1 error? Okay, so we do that in step 5. We determine if the null hypothesis is rejected first using the p-value approach. Then I'll show you the critical value approach. So what we're going to do is we're going to go to the t distribution. You can do this in a computer or a table. But we've got 149 degrees of freedom, and we've got an upper tail test. So I'm going to be interested in the area that's to the right of the value of the test statistic because it's an upper tail test. If it were a lower tail test, I'd be interested in the area that's to the left of the test statistic. And if it were a two-tailed test, I would take the value that I find in the upper tail if it were a positive t-statistic, or in the lower tail if it were a negative t-statistic, and you'll see I'll have to double it. We'll get there later. But right now what I'm going to do is I'm going to find the p-value by looking for the area that's to the right of the test statistic under the distribution of the test statistic when the null hypothesis is true. So I'm going to compare that p-value to my critical value of alpha. And if that p-value is small than the critical value, the rule is to reject the null hypothesis and otherwise fail to reject it. Okay, so I'm going to draw you a picture in just a minute. But when I looked up the p-value that is associated with our test statistic, I found an answer of 0.005. Since 0.005 is less than my critical value, my rule says reject the null hypothesis. Now, if the reason seems fuzzy to you, a picture will clear it up, and here's a picture. Okay, so this is a picture of the sampling distribution of the test statistic. If the null hypothesis is true, I'm going to be very close to 0. If X bar is much greater than mu naught in terms of standard deviations, I'm going to move out here to the right. And I'm going to, and my value of the t-statistic is going to be less and less likely if the null hypothesis were true. And if it's big enough, I'm actually going to reject the null hypothesis. So with the p-value approach, I take my test statistic of 2.58, and I look at the area that's to the right because it's an upper tail test. So I look at the area that's to the right, and I find out that that's 0.005. Well, that 0.005 is definitely less than my critical value, which is 10%, right? The value on the horizontal axis associated with the 10% area would definitely be to the left of my t-statistic. And so because this area here of 0.005 is significantly less, or is less than or equal to the area that I've chosen to represent my critical value, which is 10%, I reject the null hypothesis. I can also use a critical value approach. For the critical value approach, I'm going to do basically the same thing, but I'm going to look up T alpha in a table. So that's going to be T sub 0.10. So I'm looking for the T value that's associated with 10% of the area left in the tail, right? So I've got, the distribution, and I've got some T alpha there, and I'm picking T alpha so that's consistent with my significance level, where alpha is equal to 10%. And then I calculate my test statistic, and I see where my test statistic falls on this horizontal axis. And if my test statistic falls out here at a value greater than T alpha, I reject the null hypothesis, right? So, it really is the same thing that we did. Really is the same thing that we did previously with the p-value approach, but we're just looking at it differently. So calculate T just like before, find T alpha in a table and compare T to T alpha. And because this is a right-tailed test, if T is greater than T alpha, we'll reject the null hypothesis. I'll draw you a picture again in a minute, be the same picture we looked at before. But T alpha, if I look on a table, 149 degrees of freedom, 10% of the area left in the right tail, I'm going to find that the associated T value is 1.29. And since my test statistic of 2.58 is bigger than 1.29, I reject the null hypothesis. Here's a picture, same picture as before. Except now what I'm doing is I'm comparing T alpha, which is 1.29. I looked that up in a table, right? Alpha being equal to 0.1. There it is right up here. Alpha is equal to 0.1. And my test statistic was 2.58. And since 2.58 is bigger than 1.29, I reject the null hypothesis.